everyone. Thank you so much for coming. It's a great pleasure to introduce Evan Bauer. Evan got his PhD at the University of California, Santa Barbara with Lars Goldstein, and then spent a brief stint there as a postdoc before moving on to become the CFA postdoctoral fellow within the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. I know it's very popular these days for people to brag about the oversubscription rates of their fellowships. I think it's pretty clear the CFA postdoctoral fellow is probably one of the most oversubscribed, probably in the neighborhood of hundreds to one, not the 15 to 20 to one that people are always claiming for the Hubble Fellowship. So he's done some really very impressive work on stellar evolution, focusing on white dwarfs, binary systems, and the progenitors of type 1a supernova. And I think he will tell us about some of his excellent theoretical work today. Wait.
Thank you so much. So I guess I want to start by talking a little bit about this very vague title about stellar astrophysics and physics labs and all that. One of the ways you can think about astrophysics is using the tools of physics to understand what's going on in astronomy and astrophysical systems. But one of the ways I like to think about stellar astrophysics is kind of the reverse problem, that stars actually have really quite a lot to teach us about physics. And this is true across astrophysics, that we can learn a lot about the fundamental physics of the universe from observing what's going on out there. So today, some of the things I'm going to talk about, I think, are really nice examples of surprising physical processes that come up mostly in the context of white dwarf stars and the ways that you can use astronomical data to learn new things about physics. So let's see if this works. It turned itself off. Oh, I think it's to the arrow keys. There we go. Okay, now it's working. So of course, to start with stellar astrophysics, here's the mandatory Hertzsprung-Russell diagram, just to kind of level set and describe the parameter space that I'm going to be working in. Of course, this represents sort of 100 years of coming to understand the structure and evolution of stars. This is this nice sort of qualitative diagram from ESO that shows you the main sequence and the giant branch. And of course, stars do lots of very exciting things up here. They blow up the supernovae. And eventually, most stars don't do that. They instead shed their outer layers and end up down in this very faint region where they're very small as white dwarfs. To be more quantitative about this HR diagram, I've been really excited about sort of what this looks like in the era of Gaia, now that we have really accurate distances to a lot of stars within a kiloparsec or so. The structure of the HR diagram is really showing a lot of interesting features down in this white dwarf regime and elsewhere. And I'll get to some other regions of the HR diagram eventually. But yeah, just to do a little more level setting, Gaia is this wonderful space mission that is giving us parallaxes and proper motions for billions of stars. Those faint white dwarfs, there are hundreds of thousands of them now, just from Gaia. And of course, it does this by orbiting around the sun, along with the Earth, and these parallax measurements give us distances. And as Gaia orbits around the sun over multiple years, if the parallax changes, then we can also measure proper motions. And the precision of this is really revealing a lot of surprising structure in the HR diagram and in other ways. And so as one last piece of introduction, just want to introduce a white dwarf, just to make sure we're all on the same page. A white dwarf is basically a cooling stellar ember after something is done with nuclear burning and has shed its outer layers. Eventually it contracts to become a degenerate object of roughly constant radius. And at that point, it's just radiating away its residual thermal energy. And eventually, I guess the colors don't come through all that well on the screen, but there's this cool tool called tulips developed by Eva Laplace. Get it to run again. The color of this is actually roughly mapped to the color that the human eye would perceive as a star cools from, in this case, a white dwarf is starting at an effective temperature around 100,000 Kelvin and then cooling more and more slowly until it reaches temperatures below 10,000 Kelvin and eventually 5,000 Kelvin on timescales of billions of years. So in isolation, if you leave a white dwarf alone, this is basically what it does. It's pretty boring, right? It contracts until it's roughly at a constant radius that's set by its equation of state, mostly electron degeneracy pressure, and then it cools off. So what could be more boring than a white dwarf? But if I take you back to this HR diagram, so again, main sequence is here, giants are up here, white dwarfs are down here, and now we have lots and lots of them on the HR diagram. We zoom in, the structure that we got kind of starting with Gaia DR2 and onward is actually showing that there's a lot going on here. So there is a cooling sequence. White dwarfs start up at the top left here. This is very luminous, very hot. And the bulk of white dwarfs, the mass distribution is pretty strongly peaked around 0.6 solar masses. And so, they form this feature here, they cool along this sequence. There's kind of a bifurcation of two sequences that's mostly to do with whether the atmosphere is about hydrogen or helium. But there's also this feature called Q. And the reason it's called Q is kind of silly. It's because there are these DQ white dwarfs that refers to carbon features. Some of them happen to live roughly in this area of the HR diagram. And so they named the branch the Q branch. I think that's actually a misleading name, but I'm going to continue calling this feature the Q branch. And this sort of overabundance or pileup of white dwarfs is not formed by sort of a cooling sequence. It actually doesn't line up with the direction of a cooling sequence. It's actually formed by a population of white dwarfs cooling through this region and then slowing down for a while and piling up in that area. Off to the left of kind of the main bulk of this population is where the most massive white dwarfs live. So 0.6 solar mass white dwarfs live roughly where you see the most of these on the HR diagram. And as you go further and further left, white dwarfs get more and more compact and bluer. And so this is a feature corresponding to white dwarf cooling of the most massive white dwarfs. And that's a feature that we totally didn't know anything about until Gaia DR2 in 2018. It was pretty quickly realized that this lines up with crystallization. So white dwarfs, as they cool off, eventually their dense plasma interiors undergo a phase transition, and the plasma coupling of the ions passes a threshold that allows them to go through a first order phase transition. That phase transition releases latent heat, and so that's an extra source of energy that needs to be radiated away, and that causes their cooling to stay there. So there was really quickly a paper that came out by Pierre-Emmanuel Tremblay and several other people who have worked in the field of white dwarf astrophysics for a long time. And what they're showing here, this one plot is basically the whole result of their nature paper. It's the Gaia DR2 HR diagram for white dwarfs. These blue lines are just a handful of representative white dwarf cooling tracks. So over here is a 0.6 solar mass white dwarf, kind of the most standard boring white dwarf cooling from the top left to the bottom right. Over here's a 0.8, and I think this is a 1.0 or 1.1 solar mass white dwarf cooling track. And through using a lot of white dwarf cooling models, they were able to map out kind of where the crystallization sequence begins and ends across this mass parameter space. So the upper orange dashed curve shows where crystallization starts for a population of white dwarf. And the lower one shows where it ends, and it lines up beautifully with new feedback. So this story is really cool. It's sort of the first direct observational evidence of crystallization and latent heat being released in a population of white dwarfs. But the physics actually gets a lot more complicated than that. So one thing I said about Gaia is that you don't just get absolute magnitudes, but you also get kinematic data. So Sihao Chang, quickly after this, had a really nice paper in which he examined the kinematic data for these massive white dwarfs. And kinematics can be used as a very rough measure of age, right? Things that sit around in the galactic disk over billions of years are slowly kinematically heated. And there's a very surprising signature that instead of just looking at this space, if you look at points colored by their kinematic ages, or really just transverse velocity, so 2 out of 3 dimensions of velocity that we get from proper motions in Gaia, this Q branch feature is composed preferentially of very kinematically old white dwarfs. And that doesn't actually line up very well with what crystallization predicts. So crystallization of the models predicts that they cool for about 1 billion years. They might slow down for about another 1 billion years, and then they should evolve along. But the kinematic ages that Sihao and his paper was inferring are more on the order of 10 billion years. And they're totally inconsistent with simply a mild slowdown. And instead, what C. Howe inferred is that a subset of the population of white dwarfs pulling through this feature slow down for almost 10 billion years. And as they do that, they pause on the Q branch for a long time. So you see this overdensity form, but you also need not just to slow down mildly, but to really slow down quite dramatically, not for all white dwarfs. So if you see this animation that C. Howe made, some of them just kind of cool relatively quickly through this Q branch feature. And some of them have to slow down and pause for a very, very long time to be kinematically heated enough to match up with the Gaia data. And so this immediately reintroduced a physics puzzle. I think it's fair to say that crystallization has something to do with it. If you go back to this diagram, right, it lines up very clearly with what's happening with crystallization, but there's more to the story. Yeah.
I hate to ask this, but no, crystallization, I'm thinking of an ice cube and you have a, degenerate plasma. Can you tell us what crystallization means? That's what the physics are?
Yeah, so it's a fully ionized plasma. So even at zero temperature, the pressure ionization would keep the ions fully ionized. What's crystallizing is the ions in this plasma. So the electrons are mostly what is responsible for providing the pressure that keeps the white dwarf in hydrostatic equilibrium. But they have to carry around these ions that are most of the thermal reservoir of the white dwarf. And eventually those cool down enough that they're basically classical point charge particles. And they then are strongly coupled to their neighbors through Coulomb interactions, and they form a crystal lattice while the electrons remain free. So that's kind of, it's not an ice cube, but it is a crystallization.
Sounds a bit like a metal, actually.
Yeah.
What do you mean by kinematics here?
Kinematics, I mean the space motions of the white dwarf stars. So yeah, their velocities, their velocity dispersion in the galactic disk for the most part. Most of these white dwarfs I'm talking about are within about 200 parsecs. So this is a population of okay, so I did some work on this problem a few years ago, in which I started to use the stellar evolution code MESA to address white dwarf cooling models to try to understand this physics a little better. So MESA is an open source stellar evolution code. Hopefully some of you or many of you have seen it in stellar evolution classes or elsewhere. I'm part of the team of developers for that. I especially focus on trying to get the physics of white dwarfs right. So I immediately jumped on this problem when this started to come out. So again, right now I'm just showing the data. The Q branch feature is pretty clear. This is actually an even cleaner subset of the data. I think I limited it to white dwarfs within about 150 parsecs. And so the Q branch feature stands out as very distinct. If I go and do the kinematic, sort of just a rough cut of things that have high transverse velocities from their motions, I would argue that the Q branch feature stands out even more. These kinematically old white dwarfs really are clustering on that Q branch feature. And so MESA is something I've implemented equation of state capabilities in to understand crystallization and where that occurs. And kind of analogous to those plots I was showing earlier of contours showing where crystallization starts and ends. This is what MESA models would tell you for that relative to what's happening on the Q branch. So it lines up pretty nicely with this feature. That's a nice confirmation of that result that we saw from a different white dwarf evolution code. But actually there's a problem here so if I put in these dashed lines instead of the solid lines, the dashed lines represent where a mixture of oxygen and neon would crystallize. So this is the thing that was kind of glossed over in the Nature paper, saying that crystallization very nicely lines up with this, this feature. This feature is mostly white dwarfs that are more massive than 1 solar mass. And stellar evolution models predict that for that mass range, white dwarfs, before they burn out and become white dwarfs, they should ignite carbon and burn from carbon-oxygen cores into oxygen-neon-magnesium mixture cores. Those elements have a higher charge, meaning they're more strongly Coulomb coupled, and they should crystallize earlier at higher temperatures. And so this feature, very surprisingly, only lines up with carbon-oxygen crystallization rather than what every stellar evolution textbook would tell you. This massive white dwarf, one solar mass over here to about 1.3 solar masses over here, those really should have oxygen neon cores. And as of yet, there really isn't a satisfying explanation for why this feature is showing up where it is, other than to say we think they really do have carbon oxygen cores. And so there's kind of an open stellar evolution question as to why these white dwarfs, at least some of them, avoided igniting the carbon. Possibly it could be that they're remnants of white dwarf mergers, but even that most modeling suggests should still ignite the carbon and make oxygen neon cores. So that's one result. Here's something showing some of the MESA models I made. So these are tracks, evolution tracks of white dwarf cooling models with MESA, where I have actually included crystallization, but I haven't included yet anything to do with this cooling delay that's an order of magnitude longer. So what I'm showing are sort of white dwarf isochrones along these tracks as well, ages of half a gigayear, 1 gigayear, 2, 3. And you see that they're really the naive stellar evolution models that I would say these match up with other codes as well. They do not predict that you should have very, very kinematically old white dwarfs. These kinematic ages of sort of are on the order of 8 to 10 gigayears. And so you need things to slow down dramatically in this region to reproduce this feature. So we propose, we being Lars Bildston and Josiah Schwab and me worked on this problem for a while. And I think we pretty definitively went through the exercise of what could be the possible energy budget for these white dwarfs while they're cooling. They don't have access to nuclear energy anymore. They need other latent sources of energy. Crystallization really can't explain it. The latent heat is just not enough energy. And so what turns out to probably be the best explanation is that there are trace heavy element impurities in a white dwarf core. So a carbon oxygen white dwarf, when I refer to that, I mean that the core material is about 98 to 99% carbon and oxygen. But there are other elements left over from the primordial metallicity of the star. Neon-22 is by far the most abundant. That comes from the initial CNO abundance. CNO ends up getting processed mostly into nitrogen during the main sequence, and then that does some alpha captures and eventually makes Neon-22. And Neon-22 is kind of special because it has extra neutrons relative to its protons. And so the sort of electrons per baryon ratio or charged particles per weight, I guess is really the right way to think about it for Neon-22 is different. In the interior of a white dwarf, there's both an electric field and a gravitational field. And for ions, those are almost perfectly in balance. The hydrostatic equilibrium of the star is set by electron degeneracy. The ions aren't really playing a role. And so they're actually suspended in an electric field that counteracts gravity and keeps them from sinking. That's set up by sort of the charge coupling with their associated electrons. But because Neon-22 and some other trace things like sodium-23 have extra neutrons, they're just a little bit heavier, and so they can sink. But it turns out they don't sink fast enough to explain the cooling delay. And what I mean by that is the cooling delay is powered actually by heavy elements sinking further into the gravitational potential, liberates some energy, and is a heating source for these cooling off white dwarfs. So that's another candidate heating source. But individual ions, we think now we have a pretty good handle on the diffusion coefficients for these, and they're not going to be able to sink fast enough. So what we propose is actually that they solidify into clusters as the plasma is approaching crystallization. And this is kind of a natural explanation because we know the feature is lined up with when crystallization is happening. So we know this cooling delay happens when white dwarfs are in the regime of a strongly coupled interior that's about to go through a phase transition. And it's natural to think that elements just a little higher in the periodic table have a stronger charge coupling that might be able to form into solids a little earlier than the rest of the plasma. And then a big solid cluster, it's not too hard to work out the math of what you would expect its diffusion coefficient and sinking rate to be, and it could sink a lot faster. And that would be able to potentially provide the explanation. If you take all the Neon-22 in a white dwarf model and you let it efficiently mix toward the center during cooling, it should be able to provide enough energy for a long cooling delay, like this weird anomaly that we're seeing. So going back to this diagram, after implementing that in MESA, this is the sort of isochrone structure we got now, with the idea of Neon-22 clustering and sedimentation. And this does start to line up much better with the observations. And so the hypothesis here was that this clustering is sort of a new physical phenomena that we see in strongly coupled multi-component plasmas that could explain this structure in the HR diagram, especially the kinematic data. And it turns out that's not right. That proposal was definitely wrong. So this paper quickly stimulated some work from people who work on phase diagrams of multi-component plasma mixtures. And the cluster hypothesis was probably ruled out according to people who do like molecular dynamics, right? So you just put 10,000 charged particles in a box and you do the Newtonian dynamics between all 10,000 of them, and you can get a lot of information about diffusion coefficients and phase diagrams from that. There are some other more sophisticated methods as well. And the clustering doesn't quite work, but another idea of sort of 3-component phase separation does seem to actually be the answer. So this is still related to what we proposed. It's just a slightly more complicated fluid process in which 3-component phase separation, you could think of phase separations as something like taking a bottle of soda or Gatorade or beer, putting it in the freezer, right? It tends to freeze if you, as you're letting it go through the phase transition, right? The liquid and the solid have a different composition than each other. This is actually one method that's used to distill certain types of ciders and hard alcohols in cold climates, as some people freeze ciders and then throw, I can't remember if it's the liquid or the solid away, but you can distill, or I think it's not called distillation, but it's some way to fortify alcohol. And so multi-component mixtures, when they're going through phase transitions, they do this. And there's this proposal by Simon Bluen and some collaborators at Los Alamos National Lab that this 3-component phase separation process involving neon-22 specifically probably is the right explanation for what's going on in these white dwarfs that have this very long cooling delay. And actually, phase separation is something that people have talked about for a long time in the context of getting white dwarf cooling models, right? Not 3-component phase separation, but 2-component phase separation. So if I go to carbon oxygen and I ignore neon for a second, this is something I've been implementing in MESA really recently. I'm in the process of writing it up. So all I'm plotting here is kind of a composition profile of a white dwarf, and I'm going to show what it looks like as it evolves and freezes. So this blue is oxygen and carbon is this red line. And what happens when crystallization gets started is that you'll tend to separate into a more oxygen-enriched solid and somewhat oxygen-depleted liquid. And that actually also excites a fluid instability in the layers outside of this discontinuous boundary between the solid and the liquid. And that causes some extra mixing that will transport some of the material inward. And as you iterate through this process or continuously cool and crystallize, you end up rearranging the composition. So, you start with these profiles that are the solid lines, and you end up with these kind of smooth profiles that are the dashed lines where oxygen has been enriched in the core and carbon has been pushed out toward the surface. And that matters a lot for the energetics of a cooling white dwarf. And so this is something we need to account for in our models of white dwarf cooling and crystallization. Just the carbon oxygen phase separation is not enough to explain the cooling anomaly. You can get a delay of up to maybe 1 gigayear, but not 10 gigayears. And so I'm doing a lot more work to get all of this crystallization physics and thermodynamics fully implemented into MESA to build grids of white dwarf cooling models and use those and make those available as a tool to study populations of white dwarfs. And I'm also recently working with Charlie Conroy and Aaron Dotter, who have done work on the MIST project. Of course, June Choi did a lot of work on the original iteration of the MIST project, but unfortunately for us, she graduated from Harvard after a very successful PhD and got a job at Netflix. So not so unfortunate for her, but she's not working on MIST anymore. But I'm working with Charlie and Aaron on kind of the next iteration of MIST and then the iteration after that. And we're going to be putting a lot of white dwarf cooling physics to kind of fill out our coverage of the HR diagram with white dwarf cooling models.
Can I ask a quick question before you move on? So, you started out with this, with the Gaia data and showing that the sort of naive carbon oxygen tracks line up better than better than the oxygen neon.
Yeah.
And you put in all this other physics, and it seems like you're focusing still on carbon oxygen. What's the evidence that maybe with this other physics included that oxygen neon might not be better?
So I think pretty generically, it's just the oxygen neon crystallization happens at too high a temperature, and it doesn't line up with the feature. So, I think there is an open question there. We're going to end up making grids of stellar evolution models that kind of both carbon oxygen and oxygen neon. The most natural thing that you get if you just run MESA or other codes is kind of above that 1 solar mass. That's actually 1.05 solar masses, but above this particular mass threshold, that you should have oxygen neon. And I think we're going to need to do some more work to kind of figure out what it is. Whether is it just a subset of the white dwarfs that are carbon oxygen that then tend to form this feature, or is something really wrong with maybe our nuclear reaction rates or something that's causing us to have thought for many decades that oxygen neon is what forms in that mass regime. Yeah, okay, so this is sort of part one of the talk. I just wanted to demonstrate what I opened with, this idea of using stars as physics laboratories to learn new pieces of physics. I think particularly this crystallization physics has really been wonderfully motivated by Gaia data and this new structure in the HR diagram. And now, people like Simone Bluin making these new phase diagrams that cause what he calls distillation of neon 22. This is physics that was accessible, multi-component plasma phase diagrams. It's kind of computationally expensive, but it's stuff that we really hadn't discovered until the astrophysical data motivated going and looking much more carefully at the physics there. I'm going to quickly change gears and talk just briefly about another topic that I find really exciting that I've done some work on. So another fun feature of white dwarfs is because they're very compact, they have relatively strong gravitational fields. And I say relatively because I'm sure some of you in this room work on much stronger and much more compact objects. But white dwarfs are compact enough that they have strong surface gravities, about 1 million times stronger, almost 1 million times stronger than the gravity that we're experiencing standing in this room on the Earth, because a white dwarf is about the size of the Earth, but it's packing in almost 1 million times more mass in that volume. And one consequence of that is that white dwarfs, if you leave them alone, again, let them evolve in isolation, they form stratified atmospheric structures where the heavy elements sink away from the surface very, very quickly. So unlike the sun, right, where you see a whole spectrum, you see lots of elements at the surface of the sun or other main sequence stars. The time scale for heavy elements to leave the surface of a white dwarf can be as short as days and only as long as maybe thousands of years, and not longer than that. And so white dwarfs in isolation, we see a lot of white dwarfs like this. They are made of one element, and it's the lightest element in the star, in the atmosphere. I mean, it's, the core is mostly carbon and oxygen, but the surface, what we see, DA type white dwarfs, spectral type, have only hydrogen features, hydrogen absorption, and nothing else. And so when you dump metals onto the surface, these are called pollution because they're actually clearly supplied by some external source. So here's a nice schematic from Eric Dennehy about this. Kind of roughly the story we think about how this happens is that there are planets that somehow survive the main sequence and the AGB. They stay in the stellar system, and they're around to be able to scatter planetesimal material to within about 1 solar radius. That's like where they'll get tidally disrupted. That Roche radius, then they'll get disrupted and then form an accretion disk and accrete onto the white dwarf and give us the pollution that we see. And that pollution is actually quite common in something like 30 to 40% of white dwarfs, depending on how you do the statistics and over what temperature range and such. And this is basically, I would say, my wish list for trying to figure out what exoplanets are made of is if I could take them and put them in a blender and then sprinkle them slowly onto something hot and take a spectrum, right? What better way to get the bulk composition of a planetesimal or a planetary body? So the prototype, the most exciting system, or maybe the most historically interesting system in this field is G29-38. Here's kind of a nice diagram of roughly what this looks like. Is you have a white dwarf spectrum. There's a lot of pollution features that you can then get metal abundances out of, infer planetary compositions. There's also an infrared excess, so there's dust in this sort of debris disk from the tidally disrupted planetesimal that kind of helped fill in the picture of the debris disks, especially, I think, helped us connect the pollution of the white dwarfs to what was going on with planetary dynamics. And when we use the pollution features from the photosphere of the white dwarf, we can make stellar evolution models that tell us about the mixing timescales at the surface and then back out an accretion rate and infer how much material is being accreted and at what rate. So the kind of classic picture, a really good review article by Mike Jura and Ed Young kind of goes through, I think it has this really colorful title called Extrasolar Cosmochemistry. And I think they have a nice summary of the kind of standard picture for these polluted white dwarfs. You have planetary debris, you sprinkle it onto the surface, and then individual heavy elements diffuse and sediment through the surface layers and disappear from view. And the rate at which they diffuse kind of governs then what you back out as the accretion rate of this material. So I've done some work in this area as well, making MESA models. And we can do that modeling where we just account for individual particle diffusion and reproduce the accretion rates. But I've also argued in a couple of papers from a few years ago that some of these polluted white dwarfs are in a regime where the heavy elements build up on the surface, and then they're very likely to excite a fluid instability called thermohaline mixing. So it doesn't go fully dynamical like a Rayleigh-Taylor instability. They do mix into mostly the hydrogen-dominated atmosphere, but they're in a regime where there's this double diffusive instability that was first discovered in the ocean. So it's sometimes called salt finger convection or thermohaline salt finger convection. This is a terrestrial example that you can make in your kitchen with some food coloring and salt and warm water on top of colder fresh water. So this is dynamically stable, meaning that this material up here is not as dense as the material underneath it. But if a little bit of it mixes, because it's made of saltier stuff, heavier elements, once it comes into thermal equilibrium with its surroundings, so I take this bubble, I perturb it downward, this bubble is dynamically going to move back up this way, but if it has time to cool off, it suddenly becomes denser and starts sinking. And so it's an instability that operates on a thermal timescale rather than a dynamical timescale. But it's a pretty well understood fluid instability in the literature. And if you account for this in your white dwarf models, you infer accretion rates that are much, much higher because it causes much more mixing at the surface. So this polluting material that we see, rather than slowly sinking away, is causing a fluid instability that mixes it much deeper into the star and dilutes it further. And so you need to supply more of this material. And so what we think we're starting to see is evidence of, at least in some cases, for the youngest white dwarfs, where this thermohaline mixing is active because they're relatively hot photospheres. We think that they're being polluted at much faster rates by larger objects. And I think a kind of interesting one piece of evidence that might line up with this is there's been really cool work from Amy Bonser's group in Cambridge talking about evidence of just the composition of some of these polluted white dwarfs coming from differentiated planetesimal bodies or fragments of planets or planetesimals, where some chemistry seems to indicate more of core-rich fragments, some seems to indicate mantle-rich fragments. And the classic picture was mostly that these polluted white dwarfs were being polluted just by like asteroids, little rubble piles. But I think the evidence is starting to point toward them being polluted by larger reservoirs of larger planetary bodies. And I think there's also, I don't think I have time to really go into it, but there's some exciting results also coming out in the X-ray regime as well. So overall, the story here is that we're using white dwarfs to be able to see the composition of planetary remnants of planetary systems. We get a really wonderful amount of detail because you see individual absorption features from a lot of different elements that we think are kind of the stirred up remnants of a tidally disrupted body. And I'm doing some work with a few collaborators and with a student who worked with me last summer. Ariana Duomo is a great RU student who came to the CFA last summer, and we had a really successful project, and we're in the process of writing up another paper about one of these particularly exciting polluted white dwarfs, where we think the change in the accretion rate that we infer has consequences for an observed orbiting body around that polluted white dwarf. And I'm also working with Tim Cunningham, who's kind of been leading the charge on getting X-ray data that we think is the accretion luminosity, even though there's not very much of it. The accretion rates aren't that high, but we think we're getting an accretion luminosity in X-rays from these polluted white dwarfs. So we're going to have kind of a new lever on constraining these systems. So if you think about a polluted white dwarf system broadly, right, maybe there's this fluid instability going on. You definitely have to have good stellar evolution models to understand where there's convection, where there's not convection, if there's convective overshoot, what's happening with element diffusion. You can also have selective radiative levitation in certain temperature regimes that pushes heavy elements back out toward the surface because of their opacities in particular wavelengths, changing the radiation pressure on them. If you can model all these things, you can make interesting inferences about polluted white dwarfs. And in kind of the last section of this talk, I want to draw an analogy from that to supernova pollution. So we also are starting to find some really, really interesting stars or remnants of white dwarfs that are showing interesting evidence of having been polluted by a nearby supernova. And if we can do all of the difficult physics of modeling their surface structure appropriately in a much more extreme regime than in the case of pollution from planetesimals, I think there could be a lot to learn from these really interesting objects about the things that produce thermonuclear supernovae and compact binaries in particular. Okay, so to level set once again, going back to Gaia, I know you're all very familiar with this. As I said, we get really good absolute magnitudes from distances, and we also get kinematic data. So I talked a little bit about kinematic data of white dwarfs in terms of a velocity dispersion, things that are can have a low dispersion of 10 kilometers per second or a higher dispersion of 60 or 80 or 100 kilometers per second. And that's, we learned some interesting things about white dwarf ages from that. But Gaia is also finding much, much more extreme objects than that. It's finding hypervelocity runaway stars that are kind of on the most extreme end, things that are moving thousands of kilometers per second, because this proper motion data, in some cases, has been very quickly able to find some of the most extreme runaways that have yet been discovered. So I'm particularly excited about these two classes that were discovered shortly after Gaia DR2 based on proper motion selections and then follow up with photometry and then getting spectra. So one's called D6. This is a name that Ken Chen came up with in his discovery paper. Dynamically driven double degenerate double detonation, and I'll get into what each of those words means. And there's another class that seems to be related but different, called LP40, which is more boringly named after a prototype star that was discovered a few years ago. But both of these classes of stars are hypervelocity runaways, velocities on the order of 1,000 kilometers per second or more, that seem to show evidence of having come from a binary system in which a thermonuclear supernova occurred. So importantly, hypervelocity stars have been around for a while. Warren Brown discovered a really exciting class of things that are probably produced by the Hills mechanism in the galactic center, where you might have a binary of two B stars and they have a close encounter with Sag A star, and one of them kind of falls in and one of them gets ejected from the galactic center and can run away at comparable velocities, thousands of kilometers per second. These stars, though, their trajectories aren't pointing anywhere near the galactic center, so they need some other dynamical origin. And we're pretty confident that that dynamical origin is having once been in a very compact binary and then having a supernova occur and release that star. So focusing in a little bit on these D6 objects, so this is one of these classes of runaway stars. These are the velocity posteriors. The dashed curves are from DR2 when they were first discovered. When DR3 came out, Vedant Chandra and I checked their velocity, and we have a little more data in DR3. And reassuringly, some people didn't really believe. They thought that maybe these outliers were just kind of the most extreme outliers, and so we were selecting problematic candidates. But reassuringly, these velocity posteriors moved around by about 1 sigma, but they didn't qualitatively change, and they got a little peakier. And so we see particularly this one is about 1,000 kilometers per second. This one's over 2,000 kilometers per second. The blue D6-1 object. The green one is fainter, and so it's a little harder for Gaia to pin down, but it seems to be on the order of 2,000 kilometers per second as well. So where these are coming from? Yeah.
What are those different curves? Why are there 3 curves?
So the curves represent 3 different objects.
Oh,
yeah, these are 3 individual stars that were first discovered in DR2 and have been followed up since then. So these velocities, we're pretty confident, are coming from binary evolution, in which you have a white dwarf that's going to accrete from a companion star after spiraling in and making contact, and eventually explode as a supernova. And at that point, this star goes away, and the companion star that was donating material was Roche lobe filling and is released as a runaway star. Another way you can see this is a really nice recent simulation from Rudiger Packmore, who's at MPA. This is a double white dwarf system that he's simulating, where the more massive white dwarf is accreting from its companion, experiences a double detonation. The supernova ejecta slams into the companion, and then the companion quickly becomes a runaway star because there's no longer anything left for it to be gravitationally bound to. And just quickly to recap, the double detonation part refers to the fact that in this particular scenario, we're pretty sure that the accretor ignites on its surface because of the accretion. And so the double detonation is because of the fact that there's an initial surface detonation that initiates a core detonation that causes a full detonation of the star as a thermonuclear supernova and not just a surface detonation. So to walk through maybe the easy part of this problem is to really understand the dynamical origin and the constraints we have from the velocities. So if I have a Roche lobe filling object, we know the Roche potential pretty well, and we can calculate kind of what are the constraints that can produce a velocity like what we're seeing, right? So from just Newtonian mechanics, I've kind of put this in some weird units, but to simplify it down to having one mass as the free parameter, the accretor mass is kind of the relevant thing. That's the thing that's going to become a supernova, and then Q encodes the mass of the other through a mass ratio between the two objects. So this is just Newtonian orbital mechanics. This is a sort of Roche radius equivalent volume. So this is really just a fit to what we understand about, how big a star needs to be to fill its Roche lobe and donate to the other star. And if I put those two things together as constraint and I take these velocity posteriors, I can actually map this velocity into a size that the Roche lobe overflow constraint will allow for this object. So I'm going to start with this object that's moving at about 1,000 kilometers per second. And here's kind of, if I just jam those two equations together and say that, the Roche radius of the donor star in this scenario, according to the velocity of about 1,000 kilometers per second, here's what I get for a white dwarf donor. We don't know the mass, so I've kind of left that as a free parameter on the x-axis, but it tends to produce 1,000 kilometers per second. It needs to be able to fit within about 0.04 solar radii. And if I add on another one of these objects, the one that's moving twice as fast, it needs to be much more compact. It needs to be about 1% of a solar radius, which is the size of kind of a typical white dwarf, actually even a little smaller. So we're pretty confident that it takes double white dwarf systems in which one white dwarf makes a thermonuclear supernova and the other white dwarf runs away as a runaway star. Another independent constraint on the size of these systems, if we know that they're white dwarfs, is we actually know a mass radius relation. And qualitatively, it's pretty easy to understand in terms of the physics of white dwarfs. The pressure profile, this is what you get for degenerate objects. This is kind of just hydrostatic equilibrium. And so you get a mass radius relationship that looks like this roughly. Of course, we have more detailed models that give a detailed mass radius relation, but qualitatively what you get is that the radius scales down as mass goes up, as m to the minus 1/3 power. And if I put that on this plot, actually a more detailed mass radius relation, that's what this looks like. So the black curve is kind of a realistic mass radius relation for white dwarfs. And if I want double white dwarfs to then produce these hypervelocity runaway stars, it looks like probably I need a relatively low mass white dwarf for this one object named D62. And I need a pretty massive white dwarf for this other object, D61. And also, I haven't put it on the plot because the error bars are a lot longer and it's not very easy to interpret, but the other one is also about 2,000 kilometers per second. And so we're learning a lot just about kind of the masses of the binary systems that are producing these thermonuclear supernovae. Maybe they're representative of type 1As, maybe they're not. Statistics are still small at this point. But I think this is something pretty interesting to learn about, at least for these systems. I can also kind of rearrange this plot to put it on an axis of mass instead of radius, I should say mass versus velocity. So kind of the allowed mass range as a function of velocity for the donor star. So this is kind of the regime where for low velocities, I end up backing out a mass that's on the order of 0.2 solar masses for a white dwarf donor. And as I go up to higher velocities, I can produce something up to about 2,500 kilometers per second for the very most massive white dwarf donors. And this is pretty interesting because a normal white dwarf, sort of normal mass white dwarf, is about 0.6 solar masses. And that would predict a velocity maybe between 1,500 and 2,000. And instead what we're seeing is, this one is pretty low velocity and probably corresponds to something low mass, or maybe not the scenario at all. This one that's so high velocity really needs a pretty massive white dwarf progenitor to explain its velocity. So these are not sort of typical white dwarf systems producing these. And I want to quickly close with kind of, I think, a harder problem that I've done a little bit of work on and I intend to do a lot more work on. So rather than just kind of getting the rough geometry of these systems from the velocities, I really want to understand the detailed structure of these hypervelocity runaway stars. And if I put these stars on the HR diagram, this is a plot from Roberto Ratti's paper in which he discovered one of these two classes of stars. So again, there are two classes of runaways, and they were selected not based on where they sit on the HR diagram, but mostly just based on their velocities. But they tend to all live in this weird region halfway between the main sequence of the white dwarfs. And the velocity constraint said they had to be down here at the moment of supernova explosion. That's the only way that I can produce their really, really fast runaway velocities. But now when we observe them, they live in no man's land in the HR diagram. This means they're much more puffy. They're about a factor of 10 inflated from where they once were. So their structure is significantly altered thermally. And their composition is actually quite strange as well. So one class of simulation that I've done to try to address this is one progenitor scenario. This is actually not a double white dwarf scenario, but for the lower velocity ones, you can get away with what's called a hot subdwarf star. This is a helium burning star that basically doesn't have a hydrogen shell. So if you think of like a red clump star, but I take away the hydrogen envelope, what's left is about a 0.1 solar radius helium core that's burning helium. And I've done some work on modeling binary systems in which these come into contact and donate material, and we're pretty confident they initiate a thermonuclear supernova through that scenario. And the geometry of a system, roughly at the moment of explosion, this would be kind of what a white dwarf and a hot subdwarf donor look like to scale. Right? So the white dwarf is more massive, but also much more compact. The donor star is a little bit more extended, but this is, to scale also the orbital separation between the two. So when this goes off as a supernova, it's really going to significantly perturb this companion. And I wrote a paper with Chris White in which we focused on the companion star. So now the supernova is going to occur off frame. The white dwarf is to the left here. This is the donor star at the moment of explosion. And if you hit it with supernova ejecta, mostly what we were interested in studying in this paper was the hydrodynamics of how the thermal structure and the entropy of this object change. So you can see that the supernova strips away quite a lot of material from this. It ends up as a lower mass object, and eventually it rings down, and you are left with a pretty significant bound remnant still there. But this remnant has also had a shock traverse through the star based on the ejecta from the supernova, and that deposits entropy and changes its interior thermal structure. And so we found a way to kind of map back and forth between MESA 1D binary evolution models up to the point of supernova explosion, doing hydrodynamics in Athena++, and then mapping back into MESA to do stellar evolution on timescales of millions of years. And we kind of explored a parameter space of a few different models and explosion energies, and got a few different outcomes in terms of what the overall thermal effect can be. But in this case, the shock from the supernova can have a pretty significant effect on causing this thing to eventually inflate because of the entropy that was deposited in its core from the shock of the supernova. And so that could plausibly be part of the explanation for why these things are so thermally perturbed. Unfortunately, for the double white dwarf scenario that we need for the very fastest objects, the hydrodynamics as an explanation, excuse me, as an explanation for the inflation of the star doesn't really work anymore. The shock is just not strong enough. The white dwarf is very strongly bound. And so the perturbation to the internal pressure and entropy of the star is pretty negligible. And the white dwarf in this scenario, excuse me. In this scenario, the white dwarf does experience a shock, and it should be probably polluted by supernova ejecta. But it's very hard to actually explain why the runaway stars are so inflated. And that's an open question that I am in the process of doing some more work with Rudiger and with Ken Shen. We talked a lot about this at KITP at a program on white dwarfs last fall. And so we have some plans to work more on this problem. But it seems to really not be an easy problem. And I also quickly want to mention again, so this is what our simulation looked like when we were plotting things as density and mostly looking at the hydrodynamics. But you can also think about the composition, where now I'm kind of color coding this same simulation at the same moment by blue being donor star material and red being supernova ejecta slamming into it. And at the end of this simulation, there should be some amount of material that remains bound to this runaway object. And indeed, if you look at the spectra of these runaways, they look very heavily polluted. So even just from the discovery paper from Ken Shen in 2018, where they really only selected these based on Gaia proper motion data as runaway stars, they took low resolution spectra and they're clearly showing a lot of signs of significant pollution from these spectra. And just to kind of get a rough idea, these spectra up here are typical pristine white dwarfs that are not polluted. So again, a DA white dwarf, all you're seeing are hydrogen features. A DB, all you're seeing are helium features. These colored spectra are spectra of some prototypical polluted white dwarfs that are accreting small amounts of planetary material. And here are spectra from these D6 runaway objects. And this other class of objects that I haven't really fully gone into from Roberto Ratti's discovery paper, the LP40, they also show very heavy pollution. And Roberto has a nice paper in which they actually took high resolution spectra and did a whole lot of work to try to analyze what the surfaces of these stars are made of. And they came away with their best estimate of these, the three objects on the right are the inferences for the actual observed objects. They seem to be dominated by neon, oxygen, and elements heavier than that. And there's a little bit of carbon, but nothing lighter. There's no helium. They have pretty good constraints on helium and hydrogen, and there's none of that. So they're pretty significantly either nuclearly processed or polluted or both. And then these other things over here are sort of their attempts to compare to some simulations of nucleosynthesis and supernovae, but they don't match up very well. So I think it's kind of open question. But it's also difficult to map from, again, the state of the stars when the supernova occurred to the current state that we're observing them in. That's where really we need stellar evolution models to bridge that gap. And it kind of goes back to this difficult problem of mapping the evolution over millions of year timescales and accounting for all the different fluid mixing and sedimentation processes that we expect should be happening in these stars. So I think there's a lot more work to do in this area, and there's a lot that we should be able to learn about thermonuclear supernovae as a result. So I'm really excited to continue working on this on the hydro simulation side, and especially on the stellar evolution side, and to work with students and others who are really interested in understanding what it is that causes thermonuclear supernovae, type 1a supernovae. I think there are still a lot of really interesting open questions there. And just in closing, I'm also going to briefly mention, don't really have much time to get into it here, but I do a lot of work on binary evolution, and I think there's been a lot of exciting observational work coming out identifying progenitor compact binary systems that we think should also be producing these supernovae, and they help kind of really fill in the gaps of our understanding of kind of from birth to evolution to supernova to runaway star and how these systems evolve. So I've done a lot of work with Thomas Kupfer, who's a professor at Texas Tech now. He's been kind of leading the observational charge to discover some of these compact binaries. They turn out to be very ellipsoidally variable, so discovering them in ZTF has proved very fruitful. And I've also been working with Thomas and his student, Kunal Deshmukh, on modeling these systems more using MESA to understand the predictions that we have for these systems. And I wrote a paper a couple of years ago with Thomas predicting the period distribution and the demographics of one of the populations that we think produces these supernovae. And one of the interesting things to come out of this, excuse me, is we found that actually there should be hundreds more of these types of systems to discover And really, we're probably just scratching the surface in terms of the ones that we've been lucky enough to discover through ellipsoidal modulation up to this point. And we're really not limited by data so much as our ability to dig through all the data that ZTF has produced to discover ellipsoidal variables. And I think what's really interesting to me is, just as one example, so I've spent a lot of time talking about how over the last 5 years or so, Gaia data has introduced tons of really fun, interesting puzzles in stellar astrophysics and telling us new things about fundamental physics of stars. I think Rubin will probably be even more exciting to supercharge that with puzzles that we don't even know about yet, but the phenomenology should be really, really rich. Certainly in the transient space, where we're going to be discovering many, many supernovae and other kinds of strange and rare transients, but also in the time domain, just variable star space of pulsations and binary systems. And the challenge is not going to be so much getting the data, but then actually digging through the data and understanding what we have in that data. And I think theory and stellar models can really help guide us in what to look for in these large types of surveys, where we're getting terabytes and terabytes of data. So in conclusion, I've gone through a couple examples of the work I like to do in stellar astrophysics and the physics of stars. And this spans a pretty large range in white dwarfs, from phase diagrams that affect the populations of peacefully cooling white dwarfs, to what you can learn using white dwarfs about planetary systems, and even to the most violent transient events like thermonuclear supernovae. So I'm really excited about all the puzzles and phenomenology that we'll be able to continue to do in the coming years, especially with Rubin and eventually Lisa as well, on a much longer time scale. So yeah, thank you.
All right, we have time for a couple questions. Let's start with a long one so we can take a break and move on. Go ahead.
Yeah, what is known now about the phase diagram of a dense plasma of carbon and oxygen? For example, does it show eutectic behavior in the solidification temperatures?
Yeah, so I think that one has started, specifically a mixture of just carbon and oxygen is starting to become fairly well constrained. And this is something that people have studied for about 30 years. Okay, diagrams started getting made roughly in the late 70s. And I think the most recent work, both in molecular dynamics and also from Simone Bluen and this group at Los Alamos National Lab, they have produced kind of similar results over the last few years. So I think that one is pretty well constrained. You'll have to remind me, eutectic, this is a term that comes up a lot. And
the temperature of the mixture, of solidification of the mixture, can be lower than the temperature of solidification of the end members.
Yes, I think it sort of borders on eutectic. So unfortunately, I should have had a backup slide on this, but maybe I could sketch it out. So the phase diagram ends up looking like temperature as a function versus like temperature of the crystallization temperature of carbon, where it's like pure carbon over here and pure oxygen over here and a mixture in between. And this diagram kind of goes like this. So I think a eutectic would go like down below this line, right? But I think what you see is kind of a diagram in this.
So there's no eutectic.
I think that's right. It might be eutectic in the really carbon rich side of the phase diagram that's not so relevant for white dwarfs because they tend to be more rich. But anyway, that's my recollection off the top of my head.
Yeah, maybe at the risk of asking a stupid question on nuclear astrophysics, but I know the thermonuclear ones do not put out a lot of neutrinos, but there will be a good thermal neutrino pulse, and your little companion is sitting close by, and it will receive a good neutrino flux. I'm wondering if there's anything you can do with that to put a little heat in the center of it.
So quantitatively, I don't know the answer. I think my instinct is that, so I can maybe just flip back to the geometry of the system. Here, this is what it looks like when you have one star exploding as a supernova on the other. So I think like the this separation means you're probably not intersecting enough of the thermal neutrinos, but I don't know the neutrino physics nearly well enough to say if they could couple to some small amount of.
There's an
that
energy
needed.
source that you haven't accounted for,
Yeah.
might be something to think about.
Yeah, I think, well, okay, yeah, that's all I can say is I don't know.
Andrew, then Dave.
So you described how with the polluted white dwarfs, there's been a lot of developments in understanding the settling and mixing versus levitation rates. So obviously over time, there have been inferences that, okay, it's known what the accreted materials composition is. So should I distrust results that are from years so far in the past when we didn't have this understanding, and should I trust the results now?
So I think you should always trust them to within a factor of 2 or 3. There's a detail where in a lot of cases, the picture that we have is that some of this material is accreting and then different elements sediment at different rates because some are heavier and have different diffusion coefficients. And so basically you observe certain ratios at the surface of the white dwarf, but then you have to correct these by a factor of 2 or 3 because iron is sinking twice as fast as oxygen or something like that. So you never really need to worry about it beyond kind of that factor of whatever level. I have argued that there are some polluted white dwarfs in which, because the thermohaline mixing is dominant, there is no longer sort of the diffusive separation of some things. And so then you shouldn't be correcting for anything. You should just be using the ratios of things that are observed in the photosphere of the white dwarf.
Just one thing, Vasilis is raising his hand, but I do have a question. Your D6 runaway white dwarfs, puffy white dwarfs were sitting in this really interesting place in the HR diagram. Now, if you kind of turned it around and said, well, what if I looked at everything in that part of the HR diagram? Has anyone, like, what else could be there? And if it's only these runaway things, those can't be the only 3 things sitting there in the HR.
I think some.
Do you see what I'm saying? Like,
Yes.
Let's look at all of those.
So, I think there is ultimately a lot of, and I don't really know what like populates this, but, there's still going to be thousands of stars in this relatively unpopulated part of the HR diagram. So I don't know exactly how you clean that up. Unresolved binaries will tend to move into this region. There are sort of transient phases of stellar evolution while stars are crossing over from here over to there. I think some people have done a little bit of work trying to do selection based on some mix of kinematics and location in the HR diagram. And I actually do know of one case from a couple days ago in which Karim El Badri and Vedant Chandra were looking at a star where basically they did some, I don't know what their selection criterion was, but I think it was this kind of exercise. And I think they found another of these objects. I don't know kind of the overall picture of that, but there are more to be discovered, or at least there's one that I heard about the other day that probably will come out eventually as well.
All right, Vasilis, the the remote question option has been removed from the Zoom account, so sorry. I would love to hear your question too, but you'll have to email him.
If he emails me, I'll read it.
Oh, Buell says if you email him very quickly, he will read it aloud. We've got one more question, so type fast.
Well, I want to ask my.
Okay, 2 questions.
Go back to the wonderful Gaia HR diagram you had.
Oh, the very beginning?
Yeah, where you were inspired to go look at.
No, it's just gonna have to scroll for a while.
What I wanted to know was, it looked like you had more than one, okay.
Is this good or do you?
Well, there was, in one of the ones, it looked like there was a white gap, but like there were multiple tracks, and I was just wondering.
So here for the white dwarfs though, so there is a feature here where there's kind of a track here and a track here.
Yeah.
That is, I don't know if I probably don't have the best spot to show this, but so these are labeled as A and B sequences. It turns out those 2 features are actually white dwarfs of the same mass but different atmospheric compositions. Okay. Like I said, the white dwarf mass distribution is
they're not both contributing to your special feature.
These 2, no. In terms of spectral type, actually, a lot of these are normal DA white dwarfs. And some of them are also Q white dwarfs, and so you get the moniker Q branch, but yeah, it's kind of a
So you
different.
have to see this came through.
That one, yeah, go ahead. Big question.
A basic lattice physics question. So when you are making your crystal models or cluster models, do you consider just the Coulomb forces, or do you consider spin interactions as well?
My understanding of the literature is it's pretty much dominated by classical Coulomb forces. Yeah, so a lot of this is molecular. There's a little bit of screening from the electrons involved, but otherwise, yeah, molecular dynamics of classical Coulomb interaction point particles can reproduce these phase diagrams.
My motivation to ask this was, if you have significant spin-spin interactions, then that could lead to an extra energy liberation, and could it potentially account for your energy budget?
Oh, it's energy from spin-spin interactions.
Yes.
Um,
Because at typical white dwarf densities, your interionic separations could be of the order of a picometer.
mhm. Yeah, I'm not sure. I think the energy scale is lower than the overall sort of thermal energy of the ions, but
Okay.
Yeah, I'm not sure if that's been addressed in the literature at all.
Right, what's the verdict?
It's not here yet.
All right, well, we'll give him a chance later. So let's thank Evan again for an excellent talk.